Okay, thanks a lot, Maya. Good morning or good afternoon, wherever you are, and we'll get right started because I have 38 charts, and I'll try to speed through them, but and still try to communicate while we're doing it. So I think you've seen this chart, and Maya has explained it pretty well, but you can see the places to communicate to her if you have any issues or questions. So there we are. And again, this is just a typical. We follow the guidance of the United States Department of Defense and so forth. So what we're going to talk about is querying, qualifying, and quantifying the qualities Quagmire. And so I'll start with saying what makes qualities so much of a quagmire, and basically another way of describing them is non-functional requirements, where the functional requirements say what the system is supposed to do, and the non-functional say how well is it supposed to go. Frequently the qualities are things like reliability, availability, maintainability, but they're also safety and security that don't have ilities in their names, but there's still things that say how well your system is supposed to perform. I'll go through how we got into this project that we're doing on the qualities and finding how poorly defined and understood they were, how underemphasized they were, and how they were causing lots of overruns and failures. Then I'll talk about something that we've put together to try to address these kind of problems called an ontology, and I'll explain those. And what you'll find in the ontology is that although we wanted to have things that were sort of mutually exclusive and exhaustive, we found that maintainability was sort of key to just about everything that you want to do. And so I'll explain that, and then the rest of the talk will be sort of a deep dive into maintainability. So why are qualities important? Again, if you have a new function that you want to add, its impact on the cost and schedule is generally the cost and schedule of developing it and integrating it, which are generally additive. If you add a new quality, such as security, the impacts impact the entire system and frequently have a much bigger impact. The qualities often exhibit something called asymptotic behavior, and I'll explain that with the chart down below. Basically, this is the summary of a project that when I was at TRW, we were on contract to do, and it was something that took an information system for a large organization and took it from a department level with about 50 people to a wide campus with several thousand people. At the department level, the system worked very well with a 1-second response time, and the customer wanted the system to scale up to cover their whole organization with a 1-second response time. Once we had that in the requirements and got on contract, we tried to scale up the existing system and found that it couldn't even do 2-second response time. Since 1 second was in the requirements, our engineers came up with a different architecture, which was having 27 super MIDI computers rapidly caching information so that it would always be within 1 second of whoever wanted it. And the resulting budget was $100 million for a system that would give you 1 second response time for everybody. the customer said, oops, maybe it's not a requirement if we can't afford it. Our budget is $30 million. So what we ended up doing was with them doing some prototyping of how many people needed 1 second or how many people could do with less. And what we found was that 90% of the people could do with 4-second response time, and if you made that the main thing and then had occasional part of the queries being available at 1 second, you could build a $30 million system. So a couple of things about that. One is that the best architecture is a discontinuous function of the quality level. So if we had started and to build the system and then tune it to get faster, it never would have made 1 second. The other was that the requirements for this project were about 2,000 pages, and all you had to do was to change one character from a 1 to a 4, and the cost went from $100 million down to $30 million. So these quality things can have a huge impact on things like how much it's going to cost. Next chart. In 2012, the System Engineering Research Center was part of the DoD System Engineering Research area, and the DoD came up with a set of priority areas, one of which was called Engineered Resilient Systems, and our sponsor and the DoD people had a couple of workshops that found that most of the DoD activity was focused on physical systems, where they were doing field testing and damaging things and blowing things up and doing supercomputer modeling to see whether they could use the models as well as the field testing to reason about vehicle design and the like. The bottom line was that there were other things for cyber-physical human systems that needed resilience as well, and why didn't the SERC go and try to address those? And so we looked at a lot of the quality factors that the vehicles wanted, and also came up with a document that the Joint Chiefs had come up with that said, sampled the combat commanders and said, what qualities do you want? And they were generally not how fast and how far can the vehicle go, but how interoperable and understandable and relevant and speed could we get the information about commanding and controlling these things. So again, we tried to address that, and one of the things that we did to look at to see if we were going to study resilience, what did resilience mean? And what we found in going to Wikipedia was that there were over 20 different definitions of it. We went to a standards, or the best standards available, which was the ISO 25010, and found that it was pretty weak. And so we ended up doing an ontology to try to bring a little bit of order to the quagmire. So here's the example of Wikipedia that if you clicked on resilience, you got at least 10 different sources, and within each source there were 10 more variants within the source and so this wouldn't be so bad if it was just different names for the same thing, but what you found was that what people wanted at the end of the resilience was to bring it back to its original state, to replace a worn out battery or something like that, restoring or improving the state, maintaining the same relations, maintaining services, levels of service, functions, structures, feedback. So again, if you were going to have a multidiscipline team to try to make a resilient system, you would find a whole lot of confusion about what it was and then how to achieve it. Also, we looked at ISO 25010, which had some weaknesses like one-size-fits-all definitions. So it said, reliability is the degree to which a system, product, or component performs specified functions under specified conditions for a specified period of time. Well, if you had very precise specifications, that was probably okay, but nowadays with agile methods, frequently your specified conditions are informal sunny day user stories. And what this says, if you satisfy the sunny day user story, ISO 25010 says you're reliable, even if your system fails on the rainy day user stories. And it talks about functions. You'd think for a quality standard it would want to pass some quality criteria as well, but not mentioned, and resilience is not mentioned in the standard. The other thing is that different stakeholders rely on different capabilities and at different times and in different environments, and we'll elaborate on that. And it didn't have a very good understanding of the relationships among the different qualities, such as security. And an example of how important these synergies and conflicts are among the qualities is another large project that I was involved in reviewing, in which security was an important thing, and the project had come up with an integrated product team that tried to optimize everything to be as secure as possible. So they minimized the vulnerability profile by saying, we'll have a single agent distribute the keys, a single copy of the database. The reliability people came back and said, you have now created two wonderful single points of failure for the system. All you need to do is disable one of those, and your system is toast. It also had an over-elaborated multi-layer defense that ate up about 50% of the performance capability. It had elaborate authentication, which meant that if somebody got sick and somebody else was was supposed to take over, there were problems of finding what the password of the day was, and various things like that. And everything was supposed to be at a highest level, which means that any change that you make is going to have side effects and need to be recertified, again, which adds a lot to the cost. Another example of current practice is that frequently you'll find in a quality portion of a requirement specification something that says the system shall have a mean time between failures of 10,000 hours. Well, what is a failure? If it's 10,000 hours on liveness and you're getting 10,000 hours on liveness, but every hour several messages are dropped or garbled, the people that are relying on those messages won't think that they're getting 10,000 hours of mean time between failures. Also, the reliability will vary on operational context. Another project that I was chairing the review board of had a requirement for a response time of 5 seconds in peacetime and 2 seconds in a crisis. So do you think the workload went down in a crisis? There were fewer people hitting the system with simpler queries and the like. No, this was not a a reasonable combination of requirements. The other thing that you find is that as people are trying to manage the project, most of the things that are focused on functions. Frequently, the first big review is a system functional requirements review, and then qualities are not considered. Traceability matrices. If you have a particular function, you can trace the where in the architecture it is provided for, where in the development it is provided for, and where it is tested. If you have a requirement for a 1-second response time, it doesn't trace to part of the system, it traces to the whole system. Work breakdown structures are functional. Data item descriptions are largely functional, and earned value management is based on those, and it tends to be functional. And again, if you're trying to optimize a particular quality, what are the effects on other ones? So these are things that we wanted to come up with a better way of addressing. And we had an 8-university team that has been working on this problem since 2013, and we've had some various starts on an ontology, and then we elaborated those into an approach by exploring various ontology structures and finding that IDEF5 did pretty well for you. It basically organized the qualities into what did stakeholders value, and the things that they valued were ends, and what means were important to achieve those ends. And as we'll see, maintainability was a means for almost everything, and but it was also a way of taking all of these definitions of resilience and then finding a way that the ontology could tell you which parts of resilience you were concerned about. So, but what's an ontology? Basically, it's something that says if you have a collection of elements, here's what it means to be a member of the collection. So if you're looking at system qualities, this means that this quality identifies an aspect of how well the system performs. It also should identify the sources of variability and the value of how well. So again, the functional requirements specify what, the non-functional or qualities specify how well. So IDEF5 turned out to be a pretty good fit, and so here's what it currently looks like. It says your class hierarchy has classes and subclasses and individuals, but each element in the ontology, each software quality or system quality, has not just a place in the hierarchy, but it has indications of what are things that change the value, and what things are being referred to. Are you referring to liveness, or are you referring to correct delivery of messages? So the references are generally connected to different things that stakeholders want. States say, where are you measuring things from? And frequently what you find is if you're trying to find defects, the defect rate goes down for a while, and then you go to a new state, from unit testing to integration testing to acceptance testing to field testing to operational use. And the number of defects that you find jumps around on those. Processes similarly, and relations, again, say this system will be reliable, but if the security people might make single points of failure, you're going to have problems. The top classes cover the stakeholder value proposition. So basically, the people who are using the systems are performing some kind of mission, and they're looking at aspects of mission effectiveness. The people that are owning the system and paying for it in total cost of ownership want it to be not just effective but cost effective. It's the people who are using the system and other people like the general public, which is flying on airplanes or trusting that their credit card number won't be hacked, want it to be dependable, and as the world continues to rapidly change, you want a system that will rapidly change with it. So the subclasses say here are the means for achieving the higher class ends. So the means and ends tend to be one-to-many. Again, ideally, we had hoped that these would be mutually exclusive and exhaustive, but there were exceptions, and the main exception was maintainability, which was being relied on as a means for a lot of things. So the reference and states, processes, and relationships, take something like gas mileage for a car. The gas mileage that you want may vary by stakeholder. So the wage earner in the family who commutes 2 hours to their job will want something that has super gas mileage. The home keeper basically wants to transport the soccer team around and wants something that is big and safe, and that contrasts with gas mileage, poor gas mileage. The states, you can have a car with 2 cars with the same make and model. If one has been driven 10,000 miles and the other has been driven 100,000, you're likely to have different mileage. Or externally, if one is being used a lot for off-road and bad weather, its mileage is likely to be not as good. Processes, internal cost versus quality. Again, if you buy a car that was assembled on Monday, you tend to get a less quality car than if it's covered later in the week. Externally, again, if the car is being used to haul a whole bunch of things or being driven around wildly, its performance is going to vary. And again, there are relationships that if you want both weight and safety at a low cost, you're probably going to get something that is not very safe. So again, if we take all of those things and bounce them off the ontology, you get a different kind of definition of what reliability is. You basically say it's the probability that the system will deliver stakeholder satisfactory results. And again, this is going to be multiple stakeholders with multiple value propositions. So you need to specify who are the stakeholders and what are their desired and acceptable ranges of liveness, accuracy, response time, et cetera. What are the states that they go through? Again, we went through the various states of testing. there are various states in terms of weather and then defense condition and airplane takeoff, flight, and landing states. And again, your qualities will vary depending on what state the system is in, and it will vary in terms of what kind of processes that you're going through. And again, it will vary by what pressures are being put on this quality by people optimizing on other qualities. So again, here is the top level. The value-based means-ends hierarchy says the missions operators and managers want improved mission effectiveness. So they want physical, cyber, and human capabilities. They want it to do things quickly, do things accurately, have a significant impact, be endurable and maneuverable, scalable and versatile and interoperable. So those are all things that are qualities. Again, the investors and system owners want life cycle efficiency, which can be all sorts of scarce quantities, dollars or calendar months or scarce personnel or scarce capacity, weight, energy, fuel, and things like that. And things like manufacturability and maintainability, again, are key to those. Everybody wants the system to be dependable, which means that you'd like it to be free from defects or as close as possible to that within the budget, available, safe, secure, and so there are a number of different factors there. And surprisingly, again, maintainability comes in there in that if you build something that is reliable, but it takes a long time to repair, your availability is going to go down. So maintainability becomes a key there. And again, the world that we live in is continually and increasingly changing, and so your system wants to change to keep pace with it, or sometimes anticipate where it's going. So you want the system to be easy to change, which again means that you want to make it easy to modify or easy to repair, or you want it to independently keep track of itself and adapt to different situations. So if it's a drone running out of battery power, it can reduce some of the functions that it does and leave enough power so it can get back to its power source, that sort of thing. So here's where resilience ends up with this. Basically, it is something that says, in some cases, you want resilience to be just robust. A good example of a resilient system that is robust is the pyramids. It's sort of hard to destroy a pyramid. But there are other actors in terms of reliability and dependability that are important to getting resilience. And in some cases you want complete, but in other cases you want partial, and so you want graceful degradation, or you want to optimize on security with a little bit less in terms of cost or the like. The other aspect of resilience is that you'd like the system to be easy to change, and so it can either change itself by self-adapting and as it does trends analysis and the like, or you want it to be easy to maintain in terms of adding new features, which is modifying it, or repairability, which brings it back to its original state. And each of those depends on testability. And so one of the things that you find is that below a couple of levels, the one-to-many does not work. So testability is something that just about everybody needs. Reliability needs it, cost needs it, and the like. So again, what we were able to do with this ontology was to show what components of resilience came up with in the ontology. And so if you look at the INCOSE System Engineering Handbook, it's about the best definition that we could find, and it says it's the ability to prepare and plan for, absorb, or mitigate, recover from, or more successfully adapt to actual or potential adverse events. So you would like an ontology that says which of those are you counting on. So absorb is basically robustness. And again, you can get more robust by putting more armor on your ground vehicles, or putting triple redundancy and into making sure that if one of the processors fails, the other two can take over, or things like that. Or you can mitigate the adversity and get graceful degradation, or you can recover from it by repairability, or you can adapt to actual or potential adverse events. And again, you can do that by having the system do trend analysis and modify itself, or externally you can have the users modify it. So again, the activities in black are generally things that are done in development, but once the system is fielded, they are also counted as maintenance. So maintainability is important for all of these particular features. So let's take a look at what we ended up doing in trying to elaborate the ontology and then come up with best practices for getting maintainable systems. So why do you want to do this? Remember Willie Sutton? He was the famous bank robber who was asked, why do you rob banks? And he said, well, that's where the money is. And that's pretty much why people are concerned about operations and maintenance. The General Accounting Office said, yeah, we're spending that 75% of our information technology budget on maintenance. We ought to be able to do something to reduce it. Various people like Quentin Redmond and Harvey Koskinen have done surveys of how much of the total ownership cost goes into various kinds of hardware, and other than the things that you shoot once and never use again, like missiles, everything is up above 60%, and in the software it's generally, again, about as complex as the hardware is, and if you have a very simple thing like a thermostat that you hardly ever worry about modifying its functionality, then basically the costs of maintaining things are not so bad. However, if you look at the primarily the recent current emphasis on better buying power, fundamentally what it was primarily doing was addressing acquisition costs. and saying that we should have a should cost target, and if we start overrunning that, we should make sure that we stay within the should cost target, which may be a good idea for some things, but if you have a new security threat, you really don't want to decrease your capability just to stay within the original budget. It may be really important to add more budget to make sure that the system is not going to be useless due to poor security. So again, what we were also trying to do was to look at what is happening in the world of systems and software engineering, and what you're finding is that things are getting bigger and more complex. Internets of things and systems of systems change is changing more rapidly. Safety and security are becoming much more of a concern. Autonomy is a lot of things are going around making decisions for you, and there used to be something called the principle of human primacy that said the computer suggests and the humans decide, but in a lot of cases the computer is making decisions in microseconds and the people can't keep up. Some things are coming up that help address this, like much more ability to capture data, put it into cloud services, and do large-scale data analytics that help you help the humans address huge amounts of data coming in rapidly. But again, there are other problems in that with all of this new technology coming forward. There is a lot of challenge with the legacy software that you have, and in many cases what is happening is that it is increasing something called technical debt. So what is technical debt? It's delayed technical work or rework that's incurred when shortcuts are taken or short-term needs are addressed first. The metaphor is like financial debt, and the later you pay for it, the more it costs. It's like interest on your debt. So do it early and then save your accumulated interest. The Gartner Group said in 2010, globally, there was over $500 billion of software technical debt, and by 2015, over $1 trillion. And it's I haven't seen their latest numbers, but that's a good example of what's happening. So some technical debt is reasonable investment. If you're going for first to market, and your early adopters are a little bit willing to live with defects to be first users, then it's okay to have a little technical debt. If you're not sure quite what to build and you want to do a prototype, the prototype will have some technical debt, but that's okay. And if you have a really critical threat, like improvised explosive devices, you want to get a rapid fielding of defenses from those as quickly as you can, and you don't want to spend an extra 6 months getting all the tiny details correct. You want to get something out there that saves your soldiers as fast as possible. But on the other hand, technical debt can be lack of foresight. You may over-focus on development versus maintenance. You may skimp on system engineering. You may be hyper-agile that says, well, let's do the easiest things first, and then the hard things will become easier. That may be true for crossword puzzles or jigsaw puzzles, but usually with software, doing the easiest first means that the later things become harder. Another is that basically all of the legacy systems have been developed with not much insight into what they are supposed to do 60 years later. When I was growing up, I was a big fan of science fiction, and I really believed that by now we would have colonies on Mars and things like that. So I read books that had covers like this one here that says, City of the Future. What will the city of tomorrow be like? Here is the giant plastic, metal, and unbreakable glass city of the 21st century, a city of science, of atomic power, of space travel, and high culture. So, did we get that in 2000? No, what we really got was the picture on the right, which has one smart building in the middle of a whole bunch of legacy systems with crumbling walls and decaying plumbing and rotten wiring and things like that. So again, life cycle technology needs to address how are we going to modernize all of these legacy systems. Another challenge is that large systems become very hard to quickly manage. So this is an average of 2 large systems of systems projects that I had some data on, and basically what it said was that within groups within the system of systems, if you wanted to make a change, it was about 24 work days. Not just calendar days, but real work days. If you had to cross groups, it was 48 work days, and if you had to modify a contract, it was 141. So if you're trying to compete with an adversary, and the adversary is able to observe and orient and decide and act according to Colonel John Boyd's OODA loop, basically, you're not going to be very competitive. So what you would like to do is to find better ways to evolve systems, which again gets into how can you improve maintainability. So those are sort of the opportunities and challenges. Let's look at some of the tools for improving maintainability. So one of the things that we do for things that you want in the qualities is some things called opportunity trees. So we have opportunity trees for reducing costs or improving schedules or things like that. And then we have one for modifiability that says you want to anticipate the needs. So you want some information about how the system is going to evolve, not just what its initial operational capability is going to be. You want to do trend analysis of both itself and its environment. Other good example is a principle that David Parnas came up with that says if you want things that are easy to modify, try to encapsulate all the sources of change within individual modules so that if a change comes, its ripple effects are contained within that module and don't go and complicate the rest of the software system. Again, a lot of systems get developed without any involvement of the people who are going to maintain it, and this often leads to both building things that are hard to modify and turning the system over to the modifiers without some of the key things that they need, like the regression test and the architecture and the like. You want to design and develop, so again, you want to modularize around these sources of change. You want to be service-oriented and have loose coupling, and you want to have spare capacity, and in some cases, you want to if you know that the system is going to be in a particular domain, having an architecture that is compatible with that domain is good. In-flight diagnosis, so I'll talk about that in just a bit. And again, you want to have things that make it easier and more timely to verify and validate things. So you don't want to do all the V&V after you've built the system. You want to do it while you're building it, and increasingly what you're finding with continuous delivery that you want to be doing continuous regression testing so that tomorrow's version of the Tesla car is tested for reliability. So in some situations you will have a baseline system that has, say, 10,000 hours of mean time between failures and 4 days of mean time to repair. So a good example would be an aircraft that when it lands at the air base, some maintainers go out and check things out and determine what needs to be maintained. Once they see that, they can identify what needs to be flown into the air base to replace or modify. And it may take 4 days to get the plane back to where it can take off again. So if you had a choice of building something that was 10 times more reliable and didn't fail so much, but you still had 4 days of mean time to repair, it might be fairly expensive to get that higher level of reliability. Another thing that you could do is to find a way to reduce the mean time to repair. A good example is the F-35, which has a system called Autonomic Logistics Information System, which consists of thousands of little microsensors on the airplane that tell you whether things are corroding or running out of battery power and the like. And as it finds these, it communicates them to the airbase so that by the time the plane lands, all the things that are needed to maintain it have already been diagnosed and supplied, and so they can turn the plane around in 4 hours and get a lot more service out of it. So if you compare on availability, spending a lot of money to make it more reliable gets you from 2 nines to 3 nines, but spending money on things like the Autonomic Logistic Information System will get you much more availability and then quicker turnaround time for your airplanes. So one of the things that we addressed was, what are the synergies and conflicts among all of these different qualities, and how can we identify them and give people guidance on what will happen if you try to improve reliability by adding an autonomic logistics information system type capability, and you'll find that you get a synergy that way, that you get something that is not just more maintainable but less costly, and then giving you more service. So we came up with a set of workshops with our industrial affiliates saying, what do you think are the synergies and conflicts among these different things? And so what we've been working on is a tool that will say, if you're focusing on this, what are the synergies and that you can try to capitalize on, and what are the conflicts that you want to avoid. Again, you find that within things like dependability, there are going to be synergies between security and reliability that say, security includes confidentiality, integrity, and availability, and then those all support reliability. But if you overemphasize security and do single point of failure architectures, that you're going to have conflicts with reliability. So here is this 7x7 matrix, and there are 176 things, and so we won't go into them. And what we found was there's so many that we couldn't cover them all, so we did decide to do this deep dive on maintainability. But just to give you one example, under the effect of this dependability on resource utilization or efficiency, that more dependability tends to increase your acquisition costs. But if you look across the main diagonal, you find that total ownership cost is improved if you invest in dependability. And so we have data on things like that from the Kokomo model that says if you're building something and you're not concerned much about its reliability, you can get things that are 18% below nominal in terms of cost. If you want something that has got very high reliability, it's going to cost you 26% more for an overall 50% increase. However, Kokomo also has a maintainability cost of maintenance, and it says if you're building sloppy software, maintaining it is going to be 23% more effective than nominal. The one that's going to save you the most is if you have very high required reliability. You're going to save 19%, but you're going to still have to keep it reliable, so it's going to be a little bit more than the nominal. But that's just talking about the costs of owning and modifying the software. If the software is got defects that impact the rest of your ownership costs, like Volkswagen putting software in that gives you fake exhaust problems, and the overall cost of fixing that is more like $18 billion for Volkswagen. So in those cases, optimizing on very high is a positive impact on cost. Another thing we've been doing is looking at all of the technologies that are coming along with cloud services that enable you to analyze the history of a software project and identify what are its problems in terms of aspects of technical debt, and can you identify these and say what kind of statistics come up, like frequency of defects like code smells or complications between different quality attributes. And so what we have done is to develop a system that employs a number of different tools, like SonarQube and PMD and find bugs that address things like vulnerabilities and complexity and code smells or empty code or the like, and testing which organizations are most effective in avoiding technical debt. And so what you can see here at the bottom is that the biggest analysis that we've done had 1,363 million lines of code from Netflix, Apache, and Google, and so you can really do very large-scale, billions of lines of code analyses of these in an affordable way, and find out which organization is the most efficient in terms of technical debt. And you can get histories that say that as the system size grows, which teams are adding size and at what times, and the bottom one tracks which teams are adding or subtracting code smells. So originally the green team was putting a whole bunch of code smells in, but they worked on getting rid of them. But as you can see, there are different teams that added a bunch of code smells and didn't do much to reduce them. So this kind of thing is being used in a number of organizations to help them determine what to do about quality and technical debt of their software. Another thing we found with our workshops was that in many cases technical debt has non-technical sources. So again, organizations such as the Defense Department that have separate organizations and budgets for acquisition and maintenance frequently will find that they trim the budget in ways that make the maintenance more expensive. There are methodologies such as total quality that say you ought to be concerned with the voice of the customer. Frequently what that means is that the customer will give you loads of wish lists of things that they want, and if you buy into those, you end up with much more than was useful and something that is really hard to maintain. And if you haven't been listening to the voice of the maintainer, you will frequently get hurt by that. The conspiracy of optimism is basically that the people who get a project that they are going to outsource and own will be optimistic about how much it's going to cost and how long it's going to take to create them. So one of the things that they tend to do is to when they're outsourcing, say we're going to award the contract to the lowest cost technically acceptable bidder, who basically will be optimistic about what they will be able to build and underperform. So a good example, one of the things that we find with cost modeling is this thing called the cone of uncertainty that basically says if you don't know exactly what they're going to build, you can't really estimate exactly what its cost is going to be. And then the more you evolve into concept of operations and requirements and product design and the like, the better your ability to estimate is. And the only way that you'll find the actual or the good estimate of cost is when you finish up and see how much you spent. So a good example is the Air Force F-22 airplane, which when it got established, said we are going to deliver 750 planes at a cost of $26 billion. Several years later, as the project was canceled, it was delivering 187 aircraft, or a quarter of the airplanes, at $79 billion, or 3 times the cost. So again, these kind of things can bite you a lot. Again, if you under budget, the first organization that is going to get impacted by the budget is system engineering. A good example was a space system that was estimated as a $2 billion project. The project decided to do a good job of putting 30% of their budget into system engineering, or $600 million. It turned out at the end this was an $8 billion project, and $600 million was only 7.5% of the budget. So they really didn't have enough budget for system engineering. Other things are hasty contracts, brittle point solution architects. The vicious circle was one in which, in a couple of cases, I was involved in an architecture analysis that we decided we should bring the maintenance people in and make sure that their maintainability concerns were addressed. And so we would send this invitation out to join this team, and they would say, well, we're sorry, but because we weren't joined in the previous teams, we're too busy fixing things that could have been fixed if we'd been there before. I'm sorry, we can't make your project either. So again, there are a number of these non-technical sources of technical debt. One of the things that we decided to do was to come up with a way that projects could address these kind of things in the way that they address technology readiness. So what you see here is an unreadable complement for maintainability readiness that basically has a 9-level maturity of where you ought to be at various stages in your life cycle, and how well are you doing at the business applications of operational concepts and contracting and the like. How are you doing in staffing? How are you doing in getting maintainable methods, processes, and tools? And again, if you are at a milestone B or a preliminary design review, you shouldn't just have a preliminary design of your initial operational capability and an operational concept of how it's going to operate. You should have an operational concept of how it's going to be maintained, and who are the roles and responsibilities and workflows and budgets and schedules and the like. So if you get to the preliminary design review and you find that you're down at level 5 or 4, you should not pass the review and say we really need to make sure that these things are maintainable as well. Another thing that we've been addressing is, where are things going in the future in terms of how do people address the qualities involved in agility, making sure that your system is going to be highly safe and secure, and how can you get inside your adversary's OODA loop and by doing continuous delivery like Tesla does with its cars and various other people are doing, like Amazon getting a new release out every 11 seconds. So in the SERC talks area, earlier in the year, we had a series on agile methods for high critical systems, and Jan Bosch did a super job of saying how are summarizing his speed, data, and ecosystems book and what he is doing with the Software Center at Chalmers, which has a dozen European companies that are finding out how to do continuous delivery of their automobiles or their refrigerators or things like that. The one we had in April was Robin Yeaman, who was leading an approach that was doing agile methods, but also doing it on something that needed really high security. And so this gets you into making investments that if you're going to do continuous delivery, you need to have a continuous red team who is trying to penetrate your system and the like. So she did a super job, and again, these talks are available up at the top of the screen there at the SERC UARC website. Phyllis Marbach did something that similarly addressed things like how do you do agile methods and still do things like earn value that more frequently focus on the functions rather than the qualities. So this series is just starting with today's talk, and in October we'll have Bill Curtis, who is the Senior Vice President for CAST, which is the primary proprietor of the strongest technical debt analysis capability that is currently available, and is also the Executive Director of the Committee on Information Systems Quality. And in December, we'll have Xavier Franch, who is co-director of a similar project to ours at the SERC for the European community called Q-Rapids, which says how do we keep high quality and then do things rapidly. And so again, they've been working on ontologies and languages, so you'll get another perspective on those. So to conclude, system qualities are success critical. They're the major source of overruns and failures. Their stakeholders have value conflicts. They're poorly defined and understood and underemphasized. The ontology helps to clarify these things, but again, what we need is much more emphasis for preparing for maintainability. So there are a few references at the end that you can look at, but let's stop at the conclusions. Again, I didn't quite make the 39 charts in less than an hour, but hopefully we can have some questions and go on for a bit.
Great. Thank you so much, Barry. I'm going to repeat the first question that came in actually before we started our talk from David Gelperin. How has Agile positively and negatively influenced software quality outcomes?
Okay, well, positively, I think what people have been doing, such as what Jan Bosch and his consortium are doing with speed, data, and
sorry. Barry?
Yeah, hello.
Oh, okay, great.
Is showing that what he has is a stairway to heaven that basically says you don't try to do it all at once. You try to go from your current way of doing things to the simple parts of Agile and then the more complex parts of Agile. Once you've got through with those, you can start addressing how to do things with continuous delivery and also saying that you need not just a bunch of people that are doing the Agile, but some people that are tracking the business situation and anticipating things that need to be put into the project, and also having a test team that is continuously testing these things so that you have a reliable system when on top of all your agility. The negatives are that in a lot of cases, people, as I mentioned, say, yeah, let's do the easiest things first, and that will make the hard things easier. And so people will frequently say, well, security is a user story, so we'll just treat it with one of the other user stories and put it in one of the releases. And so, gee, we can't put it in release 1 because we haven't built anything to secure. So let's put it in release 6. And by the time you get to release 6, releases 1, 2, 3, 4, or 5 have created an unsecurable architecture. So there are positives and there are negatives to watch out for.
Okay. Jack Ring was asking about slide number 13. How do these terms apply to the socio-technical system that accomplishes systems engineering?
I'm sorry, what is the question?
Sorry, it was referencing slide number 13. How do these terms apply to the socio-technical system that accomplishes systems engineering?
Basically, they apply in saying that you want to ensure that you are addressing the quality aspects of your system as well as functional aspects, and that the socio-technical really means that you want to not just have a bunch of people who are super at programming and don't understand some of the user interaction aspects or the security aspects. So you want to have a multidisciplinary team, and you want to have a way of getting this multidisciplinary team to get to know each other and get to understand each other's skills and constraints, and create a system that is not only multidisciplinary but a good team. So that's about the best I can say, I think.
If you could possibly, Barry, jump back to slide 30 and 32. There was some clarification needed on what the slides indicate. Sorry, what the 4 lines indicate on slide 30.
So, yeah, so the blue line basically is the one that says if you're developing it, the more reliable it is, the more it's going to cost. The red line says if you're going to build unreliable systems, it's going to cost you more in maintenance. The darker red line basically says if maintainability is 70% of your life cycle cost, your total cost of ownership is going to be 70% of the way between the development and the maintenance, and so it's going to be 11% more expensive for very low reliability software in terms of your total cost of ownership. If the black curve basically says, yeah, well, suppose that your cost of making operational defects is equal to the cost of your life cycle. So another good example was the Intel Pentium chip that basically cost $500 million to develop, and could not get the square root of 2 to be a correct answer, and so they had to redo the entire system, and that cost them another $500 million. If they had addressed that early at a very high reliability, high rather than a high level, they would have gotten a better cost outcome in terms of the total cost of owning the Pentium chip. 32. Okay, 32 is basically saying that there are different management approaches in how Netflix and Apache and Google have addressed the evolution of their systems, and Apache is a more or less pure open source system where there are people who are contributing a whole lot, and other people that are contributing only little corners and sometimes not as aware of what is going on. And Netflix was something that was sort of loosely managed, and so what this was saying is that in terms of the amount of stuff that had to be done to revise and get rid of technical debt, that Google was much more efficient in terms of number of revisions per line of code, and Apache was somewhere in the middle, and Netflix was could have done a lot better.
Okay, we had a couple questions on technical debt. And let me know, Barry, if you have to jump off, because I know we've gone quite over the time. But we had a couple questions about technical debt. Technical debt seems to be large or small depending on the competency of those who have to reduce it. If so, how do you forecast relevant competency?
Yeah, that is a difficult thing to generalize because, yeah, if you're operating a system, you can do these things that track what the teams are doing and seeing which teams are adding to the technical debt and which teams are decreasing it. If you're trying to interview people and say, are these people, if they come to work for us, going to be increasers or decreasers of technical debt, I'm not sure exactly how you could probably well, just find out what do they know about technical debt, and if they've never heard of it, and then don't worry about it, and it's less likely to hire them than somebody who says, yeah, I've done the following things, and I use the following practices and checklists to make sure that I haven't put any code smells in, or I've actually used some of the code analyzers and use them before I check in my release.
Okay, I'm going to pick one more question.
Okay.
And I know we've gotten pretty long. I see words for SQ and see them defined with words, but I do not see any of the many software qualities defined with an unambiguous scale of measure as I do in my competitive engineering book. Why not?
Hi, Tom. How are you? Okay. Basically, I got all of your material, and I appreciate your review of the ontology paper, and the best I can do is say you've got a lot of stuff I need to review before I can respond to that question. So thanks for tuning in, and thanks for the question.
Okay, great. I will, Barry, thank you so much for covering all of this material. And for also promoting the own series that you're the editor-in-chief of. So thank you so much, Barry. I just had 2 reminders for those who are still logged on. I'm just going to take controls back, Barry, for 1 second.
Sure, go for it.
And hopefully everyone can see my screen. I won't go through the next upcoming talks because Barry already referenced them, but please do stay tuned for October 3rd with Bill Curtis and December 11th with Xavier French. I do want to remind everybody, for those of you who may be new to SERC or to SERC Talks, I invite you to check out our annual events, which are happening November 7th and 8th this year in Washington, D.C. It is also the 10th year of our research review, so it is quite the benchmark to arrive at, and I invite you all to check out these events and to please register, as we'd love for all of you to join the continued conversation. And for those of you who have been asking me throughout the talk, the slides are available on the SERC website, and a recording of today's session will be sent out to all those who have registered, and it will also be uploaded to our SERC Talks YouTube page. So thank you all so much, and thank you, Barry, very much for a great talk today.
Okay, thanks.
Great. Thank you, everybody.
Bye, everybody.